Hi, my name is Stephane and it is my pleasure today to take part of the training on enhanced load modeling and forecasting. I am a researcher at Lawrence Berkeley National Laboratory, or Berkeley Lab as we more commonly call it. Berkeley Lab is also a research laboratory of the US Department of Energy, similar to NREL, and it is based in California and it is managed by the University of California. Our department focuses on applied research. We develop analytical and experimental methods on tools to assess the technical, economic, and market potential of energy technologies and policies. I have been at Lawrence Berkeley National Lab for the last 17 years, and my work focuses mostly on energy efficiency, technology analysis, and policy implementation. This slide presents the outline of my presentation, which will focus on describing modeling tools that can be used for energy efficiency policy implementation. I will first describe the importance of building electricity demand, then dive into tools that support regulation, such as standard labeling and regulatory impact assessment. I will then describe building benchmarking tools, and then dive into tools that are used in integrated resource planning. Finally, I will discuss energy consumption survey and the importance of data collection. So first, why building electricity demand is so important? Well, projection from the International Energy Agency and the ASEAN Center for Energy forecast building energy demand to grow significantly over the next 20 years in the Southeast Asia region, as demonstrated by the graph on the left side of this slide. The contribution of electricity rises the most and is expected to more than double in just 20 years in the building sector, as urban citizens expand the use of appliances and cooling services in their house and their businesses. Building is the largest source of growth of electricity demand. Different policies and programs can be implemented to mitigate the impact that has growing electricity demand in buildings on the electricity system. The right side of this slide provides a list of different policies that can be implemented, categorized in three main buckets. First, regulation, which include building codes, energy efficiency standards. Then, label type policy instruments such as building certification, energy efficiency label, and benchmarking tools. And finally, market-based incentives such as utility energy efficiency DSM programs, ESCOs, financial schemes, and tax incentives. In order to assess the potential for energy efficiency and prioritize policy actions, it is necessary to conduct an energy efficiency potential studies. These type of studies are critical to increase investment in energy efficiency, and they are necessary to help to setting energy savings goals or target, quantifying the energy efficiency resource for system planning, determining funding levels for delivering energy efficiency programs, prioritize policy actions to maximize impact, and also monitoring and tracking progress and remaining opportunities, as it is shown in the right side, on the graph on the right side. The bottom-up energy analysis system, BUENAS, is a tool developed by Berkeley Lab that projects the energy demand and greenhouse gas emissions associated with the use of electric equipment through the year 2040. It is based on a bottom-up approach on the stock accounting model that takes into account sales and retirement of electric equipment in the residential, commercial, and industrial sectors. As policies and programs are implemented, the stock turnover model allows to estimate the impact on energy consumption and deducts the energy savings potential of new policy. Buenas provides a comprehensive forecast of the energy savings and emission reduction that will result from the implementation of different energy efficiency policies, notably standard and labeling programs. Regulatory impact assessments are key instruments to inform and support policy decision-making. They play a crucial role in improving rulemaking quality and promoting good governance by assessing the costs and benefits of policies. These assessments are increasingly required by governments across the world to inform decisions, to demonstrate the benefits of the programs implemented, and to make the case to advance policies. Berkeley Lab developed a tool called the Policy Analysis Modeling System, or PAMS, to provide an easy start to develop cost-benefit analysis to support the regulation of energy efficiency standards. The tool is based on the analysis that is performed in the US, but on a more simplified level. It produces a first-cut analysis of appliance efficiency programs' costs and benefits and examines the sensitivities of the analysis with respect to different policy parameters and assumptions. The methodology is a bottom-up approach where costs and benefits of efficiency standards are calculated for two distinct perspectives: the consumer perspective, which assesses the savings on electricity bills, and the national perspective, which assesses the energy saving and environmental benefits for the country. The model has built-in default values for 150 countries and has 3 appliances: room ACs, refrigerators, and lighting. This can be continually refined as more data become available. The tool is an Excel-based spreadsheet that is available freely on our website and can be tailored for specific use and also can be complemented by training. Energy consumption benchmarking is a mechanism to measure energy performance of a single building over time, either relative to other similar existing buildings or relative to a modeled building that corresponds to a specific standard, such as building codes. Benchmarking is useful to assess opportunities for improvement and quantifying, verifying energy savings. Many building benchmarking tools exist, either at the local level, the national level, or internationally. Tools vary depending on their capabilities, ranging from simple spreadsheets to custom-designed web-based tools. For example, the Building Performance Database was developed by Berkeley Lab for the US Department of Energy to help building managers and owners to evaluate the financial costs and benefits of energy efficiency improvements in their buildings. The database contains energy consumption data as well as basic physical indicators such as floor area, years built, and hours occupied from more than 60,000 buildings across the United States. Energy performance metrics include energy use intensity, for example, kilowatt hours per square foot, are calculated and individual owners can compare the performance of their own buildings to the performance of peers and to also hypothetical best practice performance buildings. The data have been stripped of identifying characteristics such as streets, addresses, to preserve business confidential information and to encourage as many private sources to contribute to the database. The tool allows users to create graphs comparing the energy use and of the buildings to the building peers group of their choice. The Better Efficiency Targeting Tool for Energy Retrofits, or BETTER, is another tool for benchmarking with an international scope. It enables building operators worldwide to quickly and easily identify the most effective cost-saving energy efficiency measures by using readily available data. It is an open-source, data-driven analytical engine, and its user-friendly web application allows users to automatically analyze building data in response to weather conditions. With minimal computing resources and minimal data entry, the tool benchmarks a building's energy use against peers in a single run. It quantifies energy cost and greenhouse gas emission reduction potential. It recommends energy efficiency improvement for individual buildings or portfolio of buildings. The tool has been used by several companies to assess the energy performance of their portfolio of buildings. This slide illustrates how bottom-up energy-saving estimates can be combined and used in energy planning. Integrated resource plans were first developed in the 1980s in response to the desire to better integrate energy efficiency into utility planning. They outline an electric utilities resource needs in order to meet expected electricity demand over a long-term planning horizon. IRP have been developed and implemented in California to better integrate energy efficiency as a resource in electricity planning. The California Energy Commission, CEC, and the California Public Utilities Commission, CPUCs, established the loading order policy in 2003. This policy sets a priority list to meet electricity needs in which electric utilities must first employ energy efficiency and conservation to meet consumer demand. Then, energy from renewable sources such as wind, solar, and geothermal. And only after all those supplies are exhausted may the utility purchase power from fossil fuel plants. The loading order, therefore, puts energy efficiency first because it is believed to be the lowest cost, environmentally preferred resource. Electricity provider must therefore implement a planning process that evaluates the potential for demand-side resource, which include energy efficiency and demand response programs. In California, the regulators have set a fund based on a small charge on electricity tariffs. This fund provides approximately $1 billion a year for implementing energy efficiency and demand resource programs. The graph on the right shows the goal that have been set by the CPUC and CEC for the years 2017, 2018, and 2019. Based on modeling analysis, the regulator determines the energy savings goals to be achieved by the utility. As you can see on the graph, utilities have systematically achieved higher savings than what the goals had set. A rigorously monitoring, verification, and evaluation program is also implemented to ensure that the savings claimed by the utilities are real and accurate, so there is no risk of under-capacity or over-capacity investment. This slide illustrates how energy efficiency modeling have been used to inform energy planning. As we mentioned earlier, energy efficiency is known as the least cost clean energy resource. But it is often overlooked due to its dispersed nature. Indeed, energy efficiency potential is not the result of one single technology, but a multitude of technological improvements across many electric equipment. Berkeley Labs' Demand Resource Energy Analysis Model, or DREAM, takes a bottom-up approach based on technology details to assess the energy, economic, and environmental impact of demand-side solutions. Future energy pathways are then developed according to technology improvement assumption, program implementation, and behavior trends to calculate the potential of demand-side programs and assess other benefits such as greenhouse gas emission reduction, pollution reduction, etc. In the graph on the right side, you can see the application of this modeling tool to forecast the load for Indonesia. The graph on the top shows the projection of stack and use load demand for a typical day. The black shaded area shows industrial motor drives, the light blue commercial demand, and the rest is all the end uses from the residential sector that tend to be concentrated at the end of the day, with lighting and air conditioners being the largest demand. The modeling tool shows that if no mitigating steps are taken, peak electricity demand is expected to move to more than triple by 2030, requiring over 50 gigawatt additional power plant capacity at a cost of tens of billions of dollars. Air conditioners, which are owned by a small percentage of households today, are expected to grow dramatically as income grows, creating the largest component of load on the peak by 2030. The graph below shows the energy savings and shows that adoption of the best available energy efficiency technology on the Indonesian market for household appliance and electric equipment could mitigate growth by 26.5 gigawatts, equivalent to 50 large power plants. So now I'm going to switch and discuss the need for good data. As most of you probably already know, that good modeling is based on the precepts of garbage in, garbage out. To avoid this statement, it is imperative to develop reliable data sets. Basically, we can say that data and analytic methods are to energy planning what lines and poles are to energy supply investment. They are the backbone of energy efficiency programs. Different approaches are available to collect data needed for different aspects of energy analysis. And I'm going to present two approaches in this slide and next that are complementary. First, energy consumption survey. Energy consumption surveys are very key to assess energy usage patterns in households and businesses. In the US, the Energy Information Administration conducts two surveys on buildings. The first one is the Residential Energy Consumption Survey, or RECS, and the second one is the Commercial Building Energy Consumption Survey, or CBEX. These surveys are conducted every 4 to 5 years and are multi-year efforts. The RECS is composed of 3 main steps. First, a household survey, then a data collection from energy providers, and finally, an end-use modeling estimation. The household survey collects data from a national representative sample of housing units and asks respondents about physical characteristics of their home, for example, such as the roofing material and the number of appliances owned, and also about their energy use behaviors. For example, how many times per week the microwave or air conditioner is on. REX collects data for more than 5,000 households in housing units statistically representative to the more than 100 million housing units in the US. The Energy Information Administration then contacts the energy suppliers for the housing unit to obtain the fuel consumption and electricity consumption and expenditure data. Finally, data are combined within complex statistical models to disaggregate consumption into estimates for end use, including space heating, air conditioning, water heating, refrigeration, etc. The chart on the right side shows some of the results of a typical energy consumption pattern in a living room in the US. Data from REX and CBEX are available publicly on the Energy Information Administration website, and they are a great resource for researchers, consultant analysts. And they are also key inputs to the US National Energy Model called NEMS. Finally, this slide is to point out to new and innovative data collection methods that can help complement the energy consumption surveys. For example, a few organizations have now developed computer algorithms to mine data from the web. These tools can be used to collect data on the characteristics of electric equipment sold on the market. For example, we have used this method to collect data to understand the energy efficiency of air conditioners, refrigerators, as well as other equipment that are sold in Indonesia. This type of information is needed to establish a baseline to assess what would be the impact if some regulation or some energy efficiency or demand response program are implemented. These data collection tools can also be used to monitor progress of program development and check for compliance rate of regulation. Other techniques also exist to collect data, such as crowdsourcing, for example. This can complement the web mining techniques by developing data collection requests in regions where online shops are not representative or for informal markets. Developing transparent and regular data collection survey and analytics are key to successful modeling and energy planning. So this slide is summarizing some of the main takeaway of this presentation. So first, we want to point out that modeling tools provide advantages for policy making by providing the analysis needed to support policy decision, assessing the benefit and cost of policy decision, providing environmental and economic impact, gathering data in a systematic manner, providing solutions for implementation. And I want also to point out that data analytics need to be supported by solid data collection method and possibly innovative methods. Thank you for listening. I hope this presentation was useful. Please do not hesitate to contact me if you have any follow-up questions, and I look forward to further collaboration. Thank you.